This video is about exponential growth functions. We're going to start by graphing one of these basic functions that's got an exponent as, or variable as the exponent. And so we're going to make a table of values, which is how we start always graphing new functions. For our x values here, we should choose -2, -1, 0, 1, and 2. So we have some things on the left and some things on the right. And then we'll use these as our exponent. So 2 to the negative second power. I'll just write it here to remind you that this means 1 over 2 squared, which is 1/4. When we plug in -1, 2 to the -1 power means 1/2. 2 to the 0 power is 1. Anything to the 0 power is 1. And then 2 to the first power and 2 to the second power. You'll notice that none of our y values are negative. So even when our x values are negative, if they become an exponent, it just turns it into a fraction. So none of our y values are negative. To plot these points, our first point is at -2, 1/4. Then we've got -1, 1/2. Then we've got the point 0, 1, the point 1, 2, and the point 2, 4. Now I know what shape this should make, so watch as I draw this curve. Since I know those y values are never going to go negative, I don't want to cross the x-axis at all and go down into the negative. So I'm going to skim along the x-axis, and then when I get to my points, I sort of shoot up to the right. It's called exponential growth. To the left, it's just getting closer and closer to the x-axis. It's not turning around. It's almost continuing in what looks to you like a straight line. It's actually getting infinitesimally closer to the x-axis as it continues out to the left. The domain for this function, it goes left and right forever, so this will be all real numbers. The range for this function, however, is restricted because it doesn't go negative. None of my y values could be negative. Our range is that our y values are greater than 0, not greater than or equal to. We never obtain a y value of 0 here, so just greater than 0. At the line y equals 0, we have what's called an asymptote. An asymptote is like an invisible barrier that the function does not cross. You don't always need to show it, and sometimes you'll be asked to show or say where the asymptote is. And so that's a barrier that this function does not cross. Slightly more complicated function, if you've got something being multiplied by your exponential term, you still want to pick the same values for x, do the exponent first, and then multiply by the coefficient multiplied by the 1/2. So do the exponent first. 4 to the negative second power means 1 over 4 to the second power, which is 1/16. And 1/16 times 1/2 is 1 over 32. This would be 1/8. 4 to the 0 power is 1. 4 to the 1 power is 4, and then we multiply it by 1/2. And 4 to the second power is 16, we multiply that by 1/2. So these functions, or each of these is a point on the function. We can graph it and see that, again, none of our y values are negative. At -2, we're only at 1/32, which is already so close to the x-axis you can hardly see. And then 0, 1/2, and then 1, 2, and then 2, 8. So here's an example of one that shoots up super fast because our base is a 4. When our base is a 4, the graph gets up really high really quickly. Whereas again on the left, it's only getting closer and closer to the y-axis, or to the x-axis without ever crossing it. So again, our domain is all real numbers, and our range is that y is greater than 0. Again, there's an asymptote at 0, y equals 0. If you've got something being added or subtracted from x, this is a horizontal translation. We've done horizontal translation with other functions before. So this is going to give us a horizontal translation of 1 unit. And because it says -1, but it's affecting the x, we go the opposite direction, so 1 unit to the right. The -3 gives us a vertical translation, and it's 3 units down. It says -3. So when I make my table for this, I still want to use the same x values, and I only want to plug them into this part of the function. So the exponent and then the multiplication, just like on the previous slide. We're going to do the exponent, do the multiplication, and fill in our table. So 2 to the negative second power is 1/4 times 4 is 1. 2 to the negative first power is 1/2. 1/2 times 4 is 2. 2 to the 0 power is 1. and 1 times 4 is 4. 2 to the 1 is 2, 2 times 4 is 8, and 2 to the 2 is 4, and 4 times 4 is 16. Now none of these points are actually on the graph, right? We're going to take each of these points and shift them 1 unit to the right and 3 units down. So I'm going to find the point negative 2, 1, and then I'm going to shift it 1 unit to the right, 3 units down, and figure out that my first point is here. Find the point negative 1, 2, shift it 1 unit to the right and 3 units down. Find the point 0, 4, shift it 1 unit to the right and 3 down. Find the point 1, 8, shift it 1 unit to the right and 3 down. And then find the point 2, 16, that's a little bit off the graph, so it would be 1 to the right and 2 down, but there's no room for me to show that. Now this time, what used to be an asymptote at 0, right, for each of the graphs we've seen before, it had an asymptote at y equals 0. This time, because we've got this vertical shift going down 3, that tells me that my asymptote is also shifting down 3. So my asymptote now is at negative 3. So now I like to show the asymptote as this invisible barrier. So I know that I'm getting closer and closer and closer to that asymptote without ever crossing it. So I'm going to write that down so you can see that word spelled out one more time. We have an asymptote at y equals negative 3. That comes from our vertical shift. So when I connect the dots, on the left, I'm getting closer and closer to negative 3 without ever crossing it. And on the right, I'm going up. So this time my domain is all real numbers, but my range is that y is greater than negative 3. Exponential growth models are how we put exponential growth into some word problems. So when a real life quantity, real life, that's what I mean by word problems. They're going to give you a scenario. When a real life quantity increases by a fixed % each year, so the value of your car or the value of an investment that you're making, it can be modeled by the general equation y equals a times 1 plus r to the t power. So you can see that the exponent is t, and that's time. That's going to keep changing. So if you want to figure out how much is your investment worth after 1 year, after 2 years, after 3 years, you can keep changing that t. What remains the same is a, which stands for the starting amount. So if we're talking population or money, it's the starting amount at the beginning, at time 0. R is the rate or the percent that you're increasing as a decimal. So if you're increasing by 5% each year, that'd be 0.05. T, we just said, stands for time, right? And Y is going to be the amount that you have at that time. So after 3 years, you plug in 3 and figure out, so how much do you have after 3 years? Let's see an example. We have a computer virus example. So in 1996, there were 2,573 computer viruses reported. During the next 7 years, the number of incidents increased by about 92% each year. We're going to write an exponential growth model for this situation. So let's start with our basic formula and fill in what we know. We're going to leave y as y. That's what we'd be trying to find. A is our starting amount. That's 2,573 is our amount at time 0, or in 1996. Our rate is a percent expressed as a decimal, so 0.92 or 92 hundredths. And time, we also leave as a variable. So you should have 2 variables, right? We want this variable here and this variable here so that it's in function notation, right? In a function, you need an input and you need an output. So our input would be time, our output would be this y. Then we can use our function in part B, where it says, so about how many incidents were there in 2003? So how many incidents were there? I'm finding y, given 2,573 as my starting amount, 1 plus 0.92, and for t, since 1996 was the beginning, or time 0, and I'll write that down so you can see. If 1996 is time 0, then 2003 is 97, 98, 99, 2000, 2001, 2002, 2003, 7 years later. So we're looking for now, how much do we have when the t equals 7? So we can plug in 7 as our exponent. We can use a calculator to evaluate this as long as you remember to round to the appropriate digits. So sometimes you're talking money, so you want to round to the nearest hundredth. In this case, we're talking computer viruses, so we're going to round to a whole number. and it comes out to 247,485. I guess they're not called viruses, they're called incidents in this problem. So that's how many incidents there were in the year 2003. Compound interest, this is an investment formula, so when you're investing money in a bank account, compound interest is a special case of exponential growth. You can see how this equation looks very similar to the one that we just used. The only difference is that it has this n underneath the rate and multiplied by the time. N stands for the number of times each year that the money is compounded. So this means when you put your money in the bank and they pay you out a certain interest rate, how often are they paying you? Are they waiting until the end of every year and just paying you your interest on December 31st? Or are they paying you this interest throughout the year? Are they paying it to you in, once in January, once in March, and so on? So the number of times each year that the money is compounded is going to get worked into the formula. Let's talk about the possibility. So it might be that your money is being compounded yearly or annually, both of these words mean the same thing, in which case n would be 1. If your money is being compounded quarterly, this means they're paying you 4 times a year, right at the end of each season, and so n would be 4. They might be compounding your money monthly, in which case they're paying you out at the end of each month, so your n would be 12. Or they might be compounding daily, for which we use 365, because there are 365 days in a year. This would mean they're paying out your interest daily. Let's see this in an example. So if you deposit $4,000 in an account that pays 2.92% annual interest, we're going to find the balance after 3 years if the interest is compounded with a given frequency. So in example A, we're going to see quarterly. So our formula is y equals the amount that you started with, 1 plus r divided by n to the nt power. So our starting amount is what we're putting in the bank, which is 4,000, times 1 plus r divided by, actually I can fill in my r, right, that's the rate. Now it's already written as a decimal, but that we still have to move the decimal back 2 places, or divide it by 100. So it'll be 0.0292 over n. Now quarterly means 4 times a year, so my n is going to be 4. My exponent is going to be 4 times, this time they give us a specific amount of time that we're leaving it in the bank for, so 3. So to simplify this, 4,000, get a complicated long decimal in here, so I'm going to leave it like that, to the 12th power, and then this you can evaluate on a calculator, and just round to the nearest hundredth because it's money. I'm going to save time and not do that, but I trust that you can put that into a calculator. If it's compounded daily, only difference is that you're going to redo this problem with a different n. Instead of paying you out 4 times a year, they're paying you out 365 times a year. So your exponent is going to be 365 times 3, and the denominator is going to be 365. And again, you can go ahead and calculate this on a calculator. Just remember to round your final answer to the nearest hundredth because it's money. And that is all.